has some sort of scope outside of C++, because of the try and accept and finally keywords that can be used in C in Microsoft situations. A significant number of the base APIs actually utilize catch-all exception handling like this to do various things, and it can have pretty interesting implications. Vista actually removes the most significant ones, but there's still some scope, especially, of course, if you've got custom applications that use try, accept, and finally. But, for example, in SP2 and Windows 2003, LSTRLen is a good example of that. They install a catch-all exception handler. So basically, LSTRLen A and LSTRLen W are intended to take a string and return a length, but they'll also fail quietly without crashing when a null or an invalid pointer is received. And they do that by using a catch-all exception handler. Now, LSTRLen A doesn't use any stack space after installing the SEH record, so it's not that interesting, but LSTRLen W does. Now, we didn't really have time to talk about scope records and accept handler 3, but the thing that's important here is that this is the SEH scope record that LSTRLen has. And the things that are important is it's got a filter function which decides which should return 1 if it's going to handle an exception, and then it's got a handler function which will run if the filter function returns 1, essentially. So you look at LSTRLen's filter function, you can see that it just returns 1 unequivocally, so it'll catch any exception, including stack overflows. If you look at the handler function, you can see it doesn't do anything really except return 0. So you can see they install this SEH record, and then they use the stack to basically push their argument and call WCSLen. So what is the problem with that? Well, basically, it's an example of how a convenient exception here can lead to a possible problem. It basically allows you to pass a valid string of any length to LSTRLen and have it return 0. And this could help you to evade some sort of maximum length check, or similarly, if it's used in some sort of allocation calculation, it can be used to allocate too few bytes. Furthermore, if it's used in a situation like passes a size parameter to something like multibyte to wide char, then you have the problems where you might have like non-terminated buffers, and depending on what the application does, that could lead to some sort of interesting scenario. So the textbook examples of how that could be misused are shown here. You can see that if vulnerable function 1 was called right at the edge of the top of the stack, you can see that you pass a string there, and it could be like any number of bytes, like 3,000 or something, and if LSTRLen catches the exception, it'll return 0, and of course that's not greater than max path, so it'll perform that copy afterwards and you'll have a stack overflow. Similarly with vulnerable function 2, it's the same sort of scenario, except like I said before, you use it as an allocation calculation. In this case, LSTRLen returns 0 and they allocate 1 byte, and afterwards there's a copy, and that's bad. So you can see a real example code of how that would look. This is from URLmon. You can see it's just like the second example I gave there, where they do an LSTRLen, allocate, and stir copy. This particular example has been fixed since we put this together, but there are numerous examples of basically vulnerable idioms throughout the Windows system libraries like this. Now, of course, you need to couple this with the ability to exhaust the stack, and that's harder, but there is definitely live examples of that as well. So other standard API functions can also be similarly afflicted. So LSTR copy W, LSTR cat W, for example, will use stack space. They have a bit of a different implication in that they can result in not doing anything to destination buffers, and you have some sort of uninitialized variable usage. In some case, the heap allocators and RTL allocate and reallocate heap functions can also catch exceptions, and that might be interesting if you need some sort of arbitrarily small allocations to fail. It only does it in certain cases though, so there's I/O routines as well, like read file, and there's a couple of others like create file where they might be interesting as well.
So when we sat down to go and look for these vulnerabilities within real applications and turn them from more than theory into, or from theory into more than theory, we found that there are some catches that you're going to run into. And we'll go through some of them here and give you some clues as to how to audit for these vulnerabilities. And really, the first thing that you need to be able to do is to exhaust the stack and end up in a situation where you're almost out of space on your thread stack. So alloc A is preferable. It's used fairly often in a lot of applications, and especially prevalent in some Windows code. And it gives you precision in that if you pass in the size to alloc A, you will control exactly how much of the local stack is reserved. And so, as opposed to recursion, which is likely to give you the ability to repeatedly reserve a fixed amount from the local stack. And so if you have a function that calls itself recursively, and the pattern could be more convoluted than that, but that's the simplest one. If that function reserves 16 bytes for its stack, you can reserve that amount over and over again as you recurse deeper. So you may be able to control the depth of recursion in order to also control the amount of stack used. But causing that stack exhaustion scenario is absolutely key. And you need to couple that with an exception handler that is going to catch that exception. And so, that exception handler can be installed prior to stack exhaustion or after it, but having one that will catch a stack overflow exception and the mixing of system exceptions with C++ exceptions is very interesting. So it's not really just as simple as that, though. You really only get one shot at this, in that if you cause a stack exception in a block of code that does not explicitly catch that exception, then your thread is likely going to terminate. Possibly your entire application will terminate at that point. And so you have to be exactly right when you do it. And so variations in the environment or the exact placement of the stack need to be accounted for and need to be exactly right. The second thing is that you can think of stack usage for a thread as sort of like a horizon with peaks and valleys, and you really need to be at the peak of stack usage for your thread, at the very top of it, when you cause the exception, and it needs to be within an exception protected block of code. So if you have a peak prior to your where you want to cause an exception that's not wrapped by an exception handler, for example, then you're going to cause an uncaught stack exception, and you're not going to get the continued execution that you want after running out of the local stack for the thread. So finding these situations can be fairly easy to do manually, but there are some calculations that you have to do to ensure that these conditions are exploitable. And all of us on stage, I'm sure, have wasted quite a few hours looking at things that look like absolutely sure bugs, only to find 3 calls back they have a stack footprint for a function that's not wrapped by an exception handler that's bigger than the one that we're looking at. So we have some ideas as to how to deal with this problem and how to automate this. We'll talk about that a little bit. But really, being at that peak of stack usage and being within an exception-protected block is absolutely key. And if you have an unwrapped peak prior to where you're trying to cause an exception, you're going to be out of luck. To go even more basic, and this is really sort of stack exploitation 101 on Windows. I could teach any of you in the room in 5 minutes if you don't know it yet. But exception handling really facilitates the exploitation of other vulnerabilities. So the SEH records are on the local stack for the thread. If you cause an exception, it walks the exception chain for that thread on the stack, and can potentially, if you bypass safe SEH checks on Windows, you just you can execute code at an arbitrary address. So this can allow you to improve the reliability of your exploits by doing them more than once if exceptions are caught. You can bypass some of the other protection mechanisms, such as stack cookies that are placed strategically near the safe frame point on the return address, address space randomization possibly, et cetera. So exception handling facilitates exploitation in and of itself, even if it doesn't necessarily introduce vulnerabilities. And another example of that is a class of software defects that isn't necessarily considered a software vulnerability in a lot of cases. And there's some corner cases like local kernel bugs or weird usage of MMUs like some ARM processors. But usually null pointer dereferences are not considered exploitable conditions. And with the ability to have continued execution after a null pointer dereference, you can have some inconsistent state within an object. There's an interesting case study of this from Scape with regards to having a stale pointer for the unhandled exception filter and then triggering a null exception, null pointer dereference within Internet Explorer. The null pointer dereference was just the way to facilitate walking the exception chain, but the continued execution that you get after a null pointer dereference when you catch all exceptions is again interesting. And it's a system exception, not a C++ exception. Another corner case that we want to throw out there that we thought was interesting was simple traditional stack overflows. Sequential byte by byte overflows of the local stack. And they are, they're very closely, as I said, they're very closely tied now to exception handling when you talk about exploitation on Windows because of things such as the GS cookie that will be right next to the frame pointer. But you'll also see that compilers do some relatively intelligent reordering of local variables. So they'll stack local buffers that are likely to or potentially contain overflows up against this cookie so that you may be able to overflow from one buffer into another and then hit the cookie, but you won't necessarily be able to hit a pointer or interesting local variables such as integers that might be used as indices into arrays, etc. So that local variable reorganization, they also do that to arguments. They copy the arguments out of their location on the stack, which will be past the return address, into very high local variables so that if you were to overflow in a local buffer, you wouldn't be able to hit the arguments. They only use the copies from the local variables. They don't use the ones that you could possibly corrupt. So it's becoming harder and harder to cause an exception that allows you to then traverse a corrupted exception chain. And one of the ways that it's most commonly done is by writing all the way to the top of the stack and hitting that unpaged address right there. And that will cause a system exception which will walk the corrupted exception chain. But if you're limited as to how much you can overflow, we have a second chance here because if you can do the exact opposite, if you can have a stack exhaustion scenario where your stack is almost entirely used up, the GS cookie handler actually has a fairly large stack footprint. And so even if you can't go all the way to the top of the stack, if you find recursion or an arbitrary stack allocation prior to causing your traditional stack overflow, you may be able to trigger an exception within the function that reports the detection of stack corruption. So you're going to corrupt the cookie, it will detect it, and then go to report it. And this function here, we've highlighted two things. It reserves a fairly large amount of stack space, 328 hex over 768 bytes. That's over average for most functions. And then after it reserves that, it pushes the flags register. So if you have gone beyond the bounds of what is left on that soft guard page and you go out of the bounds of your stack, that push-F will cause an exception, and then you'll begin to walk a corrupted exception chain as well. So this is another way to cause an exception. And it's becoming increasingly hard to do this, especially for certain vulnerabilities on Windows. Another thing that we haven't gone into, to the depth that I would have liked, but we will do more in the future of, and we've done some of it, is automation. And how do you find these vulnerabilities automatically? And there's some things that really lend themselves to being found automatically about these vulnerabilities. Things such as adding up the stack usage for a function or a set of basic blocks or a variable, traversal through a set of basic blocks. You could sit there and you can add up every 4 bytes for every push and call and, whatever each function reserves for its local stack frame. But it's very monotonous and it's not something that you'll want to do a lot of. So that really lends itself to automatic calculation. And detecting recursion as well is interesting. There's some theory around how to detect recursion on a huge list of basic blocks. It's actually, I found it interesting when I was reading up on it. It's not as simple as you would initially think, but detecting recursion can be done automatically as well. Commercially available tools out there right now, the disassembly tools, are not well suited for finding these bugs, or at least finding exploitable cases of these bugs. And the reason why that is because a lot of the commercially available tools will operate